right. Welcome, everybody, to this week's joint astronomical colloquium. The attendance sheets are so I get reimbursed for the snacks, so please put your name down. With that, I'll hand over to Joachim to introduce.
Thank you. Welcome to today's colloquium. We are very happy to have, can you hear me? You have Katja Poppenhäger here. So it's my pleasure to introduce her. Katja studied physics in Frankfurt and got her diploma from Goethe University in 2004 on a topic in theoretical physics, the Casimir effect in space-times with compactified dimensions. She then moved to Hamburg and left science and worked for an environmental agency consulting company for 3 years, and then decided to stay in Hamburg but leave this company and rather join Bergedorf, the Hamburg Observatory, and started her PhD with Jürgen Schmidt. She finished in 2011 with a PhD on magnetic activity of planet-hosting stars. She stayed on in Hamburg for about a year as a postdoc, and then she moved across the Atlantic to Cambridge and was a postdoc at the Harvard-Smithsonian Center for Astrophysics for a year. And then she got the Carl Sagan Prize Fellowship at CFA and stayed there for 2 more years. She came back more than halfway to Europe and stayed in Belfast for 3 years. She was a lecturer in Belfast, assistant professor there, essentially. And in 2018, she did the full return to Germany and came to Potsdam as a professor of Potsdam University and a group leader at the Leibniz-Institut for Astrophysics, AIP, in Potsdam. And in November 2024, she became director at AIP for stellar, solar, and exoplanetary physics as a successor of Klaus Strassmayer. We are very happy to have her here and look forward to your talk, Exoplanets, Cool Stars, and Their Interactions. Please.
Thank you very much. Yeah, thank you very much, Joachim and Catherine, for the invitation. I'm very happy to be here. It's actually been a couple of years since I've been to Heidelberg. And I don't know, just a quick question before I start the actual talk. How many of you saw the Northern Lights last night? Actually, a few of you. Nice. Okay, I didn't. So we have some plans for maybe after the talk, we will see how it goes. Joachim will say a few words. We might try and see how the evening goes. Okay, yeah, I am here today to tell you about the broad topic of my research these days, which is exoplanets, cool stars, and their interactions. And we'll start with just a little view of the exoplanet field. No, actually, we'll start with a little view of my group, which I just want to quickly introduce. This is my research group here at the AIP, where we have all sorts of people who work on the stellar part of things, on the exoplanetary part of things. We are mostly observers, but also a few more theoretical astronomers there. And I want to start with a little movie showing the exoplanet detections over the years, yeah? Actually, you see the stuff pre-1995. This is because there were, of course, exoplanets detected around pulsars before 51 PegaCb. But then you see a lot of radial velocity exoplanets popping up across the sky in sort of the early years. Thank you very much. In the early years of the exoplanet field, where it was very much about detecting that these things actually exist. Yeah? And then you start popping up here in different colors, the transit detections, the first transiting exoplanets, and what's going to pop up quite noticeably in just a little moment. You see it popping up there, and come on. Going to do big, yeah, there it is. Big splash. This is, of course, the Kepler field, where the Kepler Space Telescope stared at, and these are the big, basically catalog releases, where many thousands of exoplanets were discovered, and we can then see also some other areas of the sky where the coverage of what we detect is actually a little bit tighter than in other places. And by now, I mean, not actually now because this movie is from a few years ago, there's many thousands of exoplanets that have been detected, and not just detected, but a significant subset of those is actually amenable to detailed characterization, where we can actually try to understand the physics that's going on there. And there is a specific subset of that I like to investigate. But to understand this, we first have to see what the statistics actually look like. Sorry, this is a little bit I don't know. I'm not doing the Beyonce thing correctly here. I suppose I'm not used to the pop star microphone. Okay. The good thing is, of course, even if you look just at the transit detected ones, you can work out the geometry and basically statistically infer how many more exoplanets have to be out there, because you just see the transiting ones transiting if they are actually in our line of sight. And if you then basically do the statistical calculation, you can infer that there's typically one exoplanet or more per star in the galaxy, which is great. They are everywhere. Every star statistically that we see is actually a star-planet system, and we can study what's going on there. Now, the main detection methods, as you maybe roughly saw from the little colors there, are the radial velocity and the transit method, just in terms of number of exoplanets that have been detected that way. But of course, there are many other methods to detect and study them. The thing about this is that both of these methods actually favor small stars, which is actually quite obvious for the transiting ones, right? The smaller your stellar radius, the deeper your transit signal gets for a fixed planetary size. And also for the radial velocity method, you do much better if you have stars with sharp spectral lines, which also points you towards sort of the cool half of the main sequence, basically, where these two methods do a particularly good job, which kind of means that this cool half of the main sequence is where we have pretty good statistical coverage, and this is what we can study well. We can study the environment well that these exoplanets are embedded in. And of course, what helps us there a lot is that we have a cool star on the main sequence very nearby to us. We can study a lot of solar things and try to extrapolate what's going on in those exoplanetary systems. This, of course, has severe limitations, otherwise it wouldn't be fun, right? But we can start from here and see where stuff is going. And now we come a little bit to the types of star-planet systems that interest me and that we investigate in my group very much. And these are the ones where the planets are relatively close to their host stars. And what I've just done here is basically, so we have here a solar eclipse image in white light, sort of as the background, with an overlay of a star and a planet that I placed there, but the actual distances are the ones as they are in the WASP-12 system. We do have exoplanetary systems where the star or where the planet orbits the star in 1, 2, 3 stellar radii. These extreme close systems exist. And what we actually already see, even in this cartoonish overlay for our sun as a relatively quiet star in terms of its magnetic activity, even there, sort of in the outermost magnetic structures of the corona, this is where this planet would be orbiting if it were orbiting our own sun. And even for more active stars, we could even see more extreme environments in which those exoplanets might be. For example, if you think of M dwarfs here, yeah? Again, just a sort of cartoon montage, but if you think of these magnetically very active M dwarfs that might have extended magnetic structures, that could have strong flares, coronal mass ejections, you can even have situations where the habitable zone where your planet might be located is actually expected to be strongly exposed to magnetic activity effects from that host star. And this is where my main research interest lies and what we investigate in my group. So if I want to phrase it in a handful of research questions that keep me going to the Institute every morning with a smile on my face, basically, is we want to understand in my group, how do stars shape the exoplanetary habitats that we find them in, especially the ones that are relatively close by. Can these very, very close orbiting planets actually somehow influence their host stars? This is something that we don't see in our own solar system because we have a different architecture there, basically. We don't have these extremely close in planets. And how long do exoplanetary atmospheres actually survive in the habitats that they are embedded in? So let's go a little bit for this first question here, how these exoplanetary habitats are shaped. Something that's very important for my work, and also something where I started out back in my PhD days in Jürgen Schmidt's group, is studying the magnetic activity of low mass stars. For the sun, we of course have the great privilege to see this all in nice spatial resolution. And if we go through the different layers of the solar atmosphere, we see different manifestations of the solar magnetic activity. In the photosphere, we can see the sunspots as basically dark regions because the material that is basically trapped there by the magnetic field doesn't partake in the convection and therefore basically can just sit there and cool, and so we can see it. If we then go a little bit outwards, we see basically those same regions in the chromosphere seen in blue there in the calcium 2K line, and we can see that those regions are actually bright in the chromosphere, something we can nicely study in a bunch of spectral lines. And if you go even farther outwards, we have, of course, the coronal loops of the sun that are filled with very hot plasma of 1,000,000 Kelvin or more, and we see a strong emission from that at X-ray and extreme UV wavelengths. The magnetic activity of the sun and also other stars is variable on a bunch of different time scales. One that is depicted here is, of course, the activity cycle of the sun of 11 years duration, but also on much shorter time scales. We can see flares that strongly increase the high energy output of the stars for minutes to hours, and that can be quite extreme, actually. Now, just a little bit on the solar and stellar dynamo very quickly because I was told I was supposed to also give a little bit more background here. It's to be a didactic thing where you can get your credit points for. So a thing that is going to come into play just in a few more slides when we talk about star-planet interactions is how actually the stellar rotation interferes with the magnetic effects that we can observe. So we know for our sun that the differential rotation of the sun, both in terms of latitude and also if you go radially into the sun, causes basically time variable magnetic field via this dynamo process. And what we see is that our sun and also other stars ejects an ionized wind, which carries away angular momentum. And so over time, we get this slowdown of the stellar rotation. Typically on hundreds of millions of years to giga-years, we can actually trace this nicely in open stellar clusters. And that means, because rotation in a sense is the fuel for magnetic activity, that also the magnetic activity decreases strongly over time. And therefore, it is quite interesting to study star-planet systems that are different ages, because we might actually have an environment that's characterized by a cartoon like this one here, versus more of a solar-like environment like we might have here. So something that is investigated also in my group that I will not go into any detail is things that really directly have to do with the star itself. So we look into what stars are doing with their spin downs. There are a bunch of open questions of what sun-like stars are doing once they go beyond the solar age. There's quite some controversy in the community for the past few years whether these stars stop spinning down or not. So this is something that we are also very interested in. We also study stellar flares and had some nice successes of one of my former PhD students with locating where the flare on the star actually happens, at which latitude. And some of my people model stellar winds and coronal mass ejections, which of course also has an effect on the space weather of exoplanets. But what I really want to come to now for a while is, do planets actually influence their host stars? This is a topic that has fascinated me since early on in my career, because there were some interesting proposed mechanisms what might happen, but it has been very, very difficult observationally to see if this is actually happening. And I'm going to outline a bit of the most recent things that have happened here. So this is usually abbreviated as star-planet interactions, SPI, and the two main pathways that are discussed in the community is tidal interaction and magnetic interaction. So in the tidal interaction, I think I'm actually want to go into specific slide on that. Let me quickly check. Yeah. So in the tidal thing, which we're going to focus on first, we mainly look at direct effects on the stellar rotation, and through the dynamo mechanism also on then secondary effects on the stellar activity level. So in principle, I'm just going to give a whole bunch of references here, because this topic has been investigated for a long time without very, very conclusive observations. The idea is, okay, we have our host star here. This is the orange thing, right? And for many star exoplanet systems, especially when you're talking about hot Jupiters, you have a planet that has an orbital period of, let's say, 2, 3, 4, 5 days, something like that. And if you have a star that isn't very young anymore, typically the stellar rotation period is much longer than that. So we're talking 10 days, 20 or 30 like the sun. And so in principle, what you can have in these systems is you can have a tidal interaction where you transfer angular momentum from the planetary orbit, since it's faster, into the stellar spin. This is actually something that you can observationally show for closed stellar binaries, that stuff like this is happening. And the idea has been floating around for a really long time that on a weaker level, this should also, to some extent, be expected to happen in star-planet systems. And what should you then actually be seeing? Well, for the star, it would mean it gains angular momentum compared to a planet-free evolutionary path. And therefore, it should be spinning faster and have a slightly higher magnetic activity level than it would usually have for its age. And there lies actually the crux, because if you just pick a random field star in the solar neighborhood, it is very, very hard to pinpoint what actually its age is. You may be very lucky, you might have an astroseismic age estimate, but more often than not, you just don't know how old that thing is. And then the question is, okay, I have a star here, it's rotating moderately fast, it's moderately active. Is that because it's just one of the younger stars in the mix in the solar neighborhood, or if there's something planet-induced? Pretty hard to do. The other effect that the exoplanetary community has been looking for a long time is, of course, if that happens, what that means is that your planetary orbit is shrinking, and at some point your planet should be engulfed or disrupted if it gets close enough by the star. There's actually one exoplanet where I would say there is moderate community agreement that we are actually seeing a shrinking orbit. There's a few others that are very hotly debated, where it might be a bunch of other things that we are actually seeing. But as you can already see, this can be quite elusive. And the way I have chosen to tackle this in my group is actually to try to work around this problem with the absence of absolute ages. Yeah? So what we are actually doing is we look at wide binary systems of stars, which are co-eval, and one of them has a known planet and the other one doesn't. And in that case, yes, you still don't have an absolute age, but you can actually compare what is the discrepancy in rotation and activity of those two stars. And if you do that for a large enough sample, if it's always the one with the planet that is more active compared to the negative control star, so to say, you actually get a statistical signal that you can trace back to a planetary influence. And this is actually something that one of my former PhD student has investigated here. Her name is Nikoleta Ilic. And what she has done is she has selected a sample of wide binary systems, and I think the actual catalog came from your group. That's what I think, from the Gaia wide binaries. Anyway, and we looked at the ones that have close-in planets. Actually, the ones that have close-in planets are sitting here, where we expect a strong tidal interaction. Also, the ones where the planet is farther out, where we basically don't expect a strong effect being here. And what you're actually seeing on this plot is the measured magnetic activity discrepancy between the star with the known planet and the other star in the system. And you do see a whole bunch of scatter. But overall, you do see that there is a statistically significant trend in the sample. It's not just a data blob like this, that typically the stars with the hot Jupiters tend to have higher X-ray activity. We measured this in the X-ray band because it's very sensitive to these activity differences, than the other star in the system. And this is quite interesting because to our knowledge, this is the first time that we were able to switch off the typical biases that exist and that many of those papers I had listed on the right-hand side had tried to work around in other ways. And this is really an interesting thing here. This should also mean that here in this part of the plot, there should be planets that should over time slowly shrink their orbits. The other pathway of star-planet interaction that has been looked at mainly on the theoretical side, but also partially in observations, is magnetic star-planet interaction. So typically, you know, Jupiter has in our system a relatively strong magnetic field. We can have stars that can either be highly active if they're relatively young or that are relatively quiet. There can be magnetic reconnection events. There can also be more subtle effects where maybe your planet passing by could just sort of wiggle stuff around and trigger some effects that otherwise would have happened at other times on the whole star. And what we would be looking for there is episodic activity features of some kind that are different from what the star would be doing normally. And this is, of course, relatively hard because the stochastic activity, we have a hard time predicting when a star is going to flare, but we can try and look for planet-related periodicities and not stellar rotation-related periodicities. There's also vast literature on this. And I think the original paper by Evgenia Shkolnik is this one here, where there was a first hint of something like this. So what we're seeing here is measurements of the stellar activity in chromospheric line emission. And actually, in the first set of epochs that she had observed, this actually followed quite neatly this sort of ad hoc shape, basically, that she drew through there to guide the eye. What you're having here is basically the orbital phase of the planet, which is different from the stellar rotation period. So basically, they were seeing, there's a bump of elevated stellar activity and seems to come around every time the planet comes around. But then actually in their second observing period in the next year, basically it wasn't doing that thing anymore. And so it's like, yeah, this is hard when stars do stochastic stuff. Is there something? Is there nothing? It's very difficult. And a lot of people have tried to hunt for this. And apparently the size of these effects seems to be not overwhelmingly large compared to other things we typically see that are happening on the star. However, I want to show you one thing that we are very happy with. So one thing that has changed in this game, I would say in the past 10 years or so, is that there is a huge amount of data available now on light curves of stars. This is something where in the past you basically had to go and you have your star with the planet and you point it there with your spectrograph and you collect the spectrum. But if you go for light curves, you can actually search for flares. And what we have here is this is actually a Kepler light curve, so a relatively old one, of an active star. And this is an M dwarf. What you can see is modulation by the stellar rotation, but all these little things here are various flares that are happening on that star. And if you compare it there to a little movie of the sun, our sun doesn't flare nearly as often. But the idea is, okay, now we have this data set where we have many, many flares and we can just basically count them in the light curves. Can we find planet-related periodicities there? And for that, you need these large numbers of flares to actually hope to find something. And this is where also former PhD student and postdoc of mine, Ekaterina Ilin, comes in. And she actually investigated this. She selected, so maybe I should say for context, there are two different schools of what target you should choose to try and search for that. One school of thought is, okay, let's go for a really magnetically quiet planet, because then anything that the planet might trigger at least shows up against a very low background of what the star is doing elsewhere or doing other times. The other school of thought is, well, I mean, just from the geometry, maybe it's better to go for a really active star that has much more extended magnetic structures in its corona, because then it's more likely that the planet has something it can trigger. So let's go for that. And we actually went for that second option here. We went for a relatively young sun-like star with a gas giant planet in a short orbit. And we had some interesting, promising early results with TESS, and got Cheops observations, so a space-based light curve in both cases, to complement this and study this in detail. TESS has usually the advantage that you get relatively long chunks of light curves. Cheops can't stare as long, but is from the bandpaths bluer, where your flares show up more nicely. And so we have 70 days total that we have covered the system here. And we expect to see a number of things in the light curves, and I'm going to show you a few of those. So these are typical TESS light curves that we are seeing here, and the main signal that you're seeing is the stellar rotation that just shows up kind of like a sinusoidal modulation. it comes from the spots on the stellar surface. You see a little bit of evolution of the spot patterns, yeah, because here that pattern changes somewhat. You also see in this light curve the times when the transit of the planet happens. Here's such a transit. Here it's a little bit harder to see because it's sort of overlaid on what else is happening on the star. So there's transits of the planet, and there's a whole bunch of little flares that I'm going to zoom into just a moment. Those are basically these orange lines here where the little upward blips are happening. And so this is just some part of the data, and our expectation is, okay, if the idea is if the planet is continuously triggering flares on the host star, it's kind of like a lighthouse, yeah? When it comes around to this side, you're going to see the flares, the extra flares that are being triggered, and when the planet is back here, then they're basically on the side that you can't see. Here's some examples from those Cheops light curves that we collected. Cheops does this snippet-like thing, but we actually also do catch a bunch of flares here. These are the test ones, some of the test ones zoomed in. You typically have this very standard shape in white light curves where you have this very steep exponential rise and then a longer exponential decay of these flares here. And maybe I should say there's a bunch of good codes now around to more or less automatically detect those in light curves if they're relatively well behaved. So, and now the big question is, of course, do we see a lighthouse effect? And in this plot, basically what you're having is, so this direction is towards the observer, and these bars here show you basically the flare rate that we observe in these 70 days. And if you expect that there are only planet-triggered flares and the star doesn't flare at all if there are no planet-triggered ones, then basically what we expect just from the viewing geometry is that these rates would kind of follow this one here, this orange blob. And what you do see is, it doesn't exactly follow this because of course the star also does some stochastic flaring. It also flares sometimes when the planet is behind because that's what stars do. But this is something you don't expect from a star that just displays stochastic flaring. There's actually strong evidence that there's an elevated flare rate here whenever the planet is in front of the star. And this is something that was very, very exciting. It is a relatively strong effect. So the flare rate of the star is 5 times larger on the side that faces the planet when it goes around. This is also interesting for people who are mainly interested in the exoplanets, because that means that this planet is actually creating a hostile environment for its own atmosphere. It's getting blasted with flares much more than it would usually be if it were just a bit farther away so that it couldn't influence the host star here. Yeah, this is something we're very excited about. And there's a few other targets that have similar properties to this system here, and that we're going to investigate in the future. Something that is quite important to us here is, of course, now we know, okay, there's more flares, but in principle, one can also imagine these flares might look different if you look at them in more detail. Yeah? You might see different energetics, you might see different loop lengths possibly, and this is something where Ekaterina Ilyin has recently been granted a large observing program in soft X-rays with the XMM Newton Space Telescope, because this is exactly the kind of stuff that you can probe in X-rays from your flare decay times and so on. So we're quite excited about this. Okay, now I want to change gears a little bit here and come to exoplanet atmospheres and their survival. Because I've already hinted at it on the last slide. If you create a hostile environment for yourself, well, you have to worry about a bunch of activity effects. And just maybe a little bit for context, I think many people here, of course, know this, but just to call it, to recall it here, our main ways of studying exoplanet atmospheres is through transits and through eclipses. So we can see basically the starlight getting filtered through here, this terminator, this part of the atmosphere of the exoplanet when we are during the transit. And as we go around, we basically see the thermal emission and also some reflected starlight just before and after the planetary eclipse is happening. And we can study this in a variety of ways. Some people do this with low spectral resolution, for example, with James Webb. In my group and at my institute, a lot of people do high resolution spectroscopy to do these kinds of things. And this is one of these examples here. So, for example, with the PEPC spectrograph at the LBT. You can collect these high-resolution spectra, and then you can basically probe for absorption features that come from your planetary atmosphere that is sitting in there. And these signals tend to be very, very small. So what the community is typically doing is that you can basically add up your signal in smart ways. So what you're basically having here is you have your spectral lines from the star, which, if you put all your spectra into the reference frame of the star, are represented by these straight lines going up and down here. However, the planet is, of course, moving around, and with it, you get basically a radial velocity shift, not of the star as it moves around, because we're in the stellar rest frame, but basically the planetary atmosphere, both an emission and an absorption, has a bunch of RV shifts that follow basically the orbit around. And this is these sort of sinusoidal shapes here. And so during your transit, you know basically that you can add up your signal if you have a time series of spectra that go along this slanted path here. And then you know this is actually your exoplanetary atmosphere signal and not a stellar signal or a changing stellar line. And while you're out of transit, you can also do this with emission lines. And this is something that is a very successful technique. There's interesting things that you can get out of that. For example, you can, by the separation of the stellar and the planetary rest frames, you can detect a bunch of different atomic species in the exoplanetary atmospheres. Here's for the ultra-hot Jupiter KELP 20b. Now, if you, sorry, I have to check here that I don't make so many crunchy noises. If you want to do this not just for the hot exoplanets, but you want to go to more temperate worlds, so you're going towards habitable zones, then you really run into some limitations with the current instrumental capabilities. You have, of course, typically you will be looking at smaller planets, you will be looking at cooler planets, therefore more compact, heavier atmospheres, so your signal gets really, really quite small. This means currently you can't do this really, but when you go to really large mirror sizes, for example, for the ELT, you have actually this within grasp, and you can try to study what is actually going on in the temperate exoplanet atmospheres. This is something where my institute is actually quite active. So there's the high-resolution spectrograph ANDES for the ELT, which is being built by a large consortium led by Italy, and we at the AIP are actually developing the blue part, the so-called blue subsystem under the UBV. Here's actually from a recent meeting with our colleagues from Spain and from Switzerland, where we collaborate on developing this. And what is very interesting also for us on the stellar side is that this part of the spectrograph that we are developing also contains the calcium-2 H and K lines, which are very, very sensitive stellar activity tracers. So we actually get a view from the stellar activity all through basically the near infrared, where we can look at absorption features or emission features of smaller exoplanets. Now this is a little bit cut off. Now I want to tell you a little bit about basically what keeps me very busy since half a year ago, because I have a new ERC project in my group, especially where it's about exoplanet evaporation. This is something that, is always fascinating to me, and where a bunch of things actually comes together from the stellar side and from the exoplanetary side. So when you start out with your typical exoplanet, typically start out with a hydrogen-helium atmosphere, and you can lose some of that atmosphere, especially if you are strongly irradiated by your host star, and maybe you end up still being a slightly lighter hydrogen-helium atmosphere exoplanet, or maybe you lose all of that initial atmosphere and you can outcast a secondary atmosphere. And then a lot of really interesting things can happen in terms of habitability and how we understand the star-planet systems around us in that regard. Now, to probe how this evaporation of hydrogen-helium atmospheres is going on, there's some cool techniques going on observationally that also really require a bunch of dedicated stellar knowledge. You could try and observe, of course, the escaping hydrogen. It's the most abundant element. People have tried this early on. This tends to be observationally really, really tricky, because basically Your hydrogen lines of the star can be quite variable. Let's say you go to Lyman alpha, it's a UV line, star is variable. Then it goes to the exoplanetary atmosphere that is maybe escaping. You can probe that, get an absorption signal, and then you still have to go through the interstellar medium, which imprints its own absorption signatures. Then you have to worry about the geocorona when you want to observe this with Hubble. This is really, really messy. People have tried this to measure this for more than 20 years, and there's 5-ish exoplanets where you can actually measure this signal in hydrogen. It's really, really challenging. But 8 years ago now, something that has become way more popular actually, and this is to observe helium signatures of your outflowing atmosphere. This is actually originally was proposed by Sarah Seeger in I think a 2001 paper, and then due to various challenges was never done until Antonia Klopčić actually repopularized this in 2018. So the idea is, okay, you have your helium, right? And typically, you would say, okay, I have my helium, I just see a transit signature without the atmosphere, because there's something really interesting with helium. There's something called the metastable helium lines. You can actually put helium in a metastable state so that it produces absorption lines in the near infrared. And this is really cool, because if this happens, then in the near infrared, you can actually trace this outflowing atmosphere. How do you get your helium into the metastable state? Well, we actually know this from the sun. It can be for stellar atmospheres, you have 2 pathways, but the one that's relevant for exoplanets is you basically ionize your helium with incoming extreme UV photons from the star, and when it recaptures the electron, you get actually a whole bunch of them ending up in this metastable state. That's observable. And then you get signatures like this. So if you have helium outflowing or in an extended atmosphere in the metastable state, you go to that wavelength, you basically see a significantly deeper transit profile at that wavelength. This has been very successful in those past 8 or so years. So there have been many, many detections, way more than in hydrogen lines, of these extended atmospheres. Now, that's neat, but if you want to go from your helium transit to the actual physics of the atmosphere, there's a few more steps involved. Because what we kind of, let's say we want to know what is the amount of the evaporating atmosphere that you have there. What we actually measure is what's flowing out there times, well, what fraction of my helium is actually in this metastable observable state versus stuff that is in any other state. And therefore, we need to figure out how much helium in the metastable state do I actually get. Or you could say, okay, well, if you do it via ionization with extreme UV photons, well, then we just measure that, right? And the problem with that is that basically at those wavelengths, your ISM is practically opaque. We have very, very few stars for which we can measure this part of the extreme UV spectrum. They are all within 10, 15 parsec, basically, and the last mission that did that was EUVE. So this is a severe challenge, actually. You can try to sort of extrapolate from other parts of the stellar spectrum, but it can get really tricky. And I want to show you this in this plot here. So it's already a couple of years old, but it illustrates it nicely. What you see on this plot is on the y-axis, basically the atmospheric helium absorption of the planet in scale height. So you kind of normalize over different stellar planetary parameters. And here you have sort of a broadband estimate of the incident XUV flux that the planet receives. And in principle, this part here you would kind of expect, yeah? You go to higher fluxes, you should get more helium in your metastable state, and you get successively deeper transit features in those helium lines. And then the problem arises that all these guys here don't play along. And this is surprising because they are actually very much hydrogen-helium giants. There's many good old friends here, HD1 and 9733. Yeah, these are hot Jupiters. Why are they not playing along? And this is something we are doing a deep dive now in my group to investigate this in detail, because you have to really put all your stellar knowledge about the stellar corona in there to try and do a good estimate of what's actually happening there. So no helium signature, no atmosphere is very obviously wrong for these guys here. We need to figure out why this atmosphere is not in the observable state. Here is a little bit of an outline of what we're doing. We basically started a little bit more than half a year ago, this team, and what we're actually doing in there, and that I'm very excited about, is we're actually trying a novel reconstruction of this part of the extreme UV spectrum of the star to really pin this down and to basically get rid of a bunch of uncertainties that are currently floating around with a bunch of methods. And then we actually built on a bunch of models for outflowing exoplanet atmospheres and then compare this to observations. I want to just a little bit tell you about this because in my truest heart, I guess I started out as an X-ray astronomer and I still like this very much. There's something really cool about the part of the EUV spectrum that's relevant to the exoplanets, and this is that it happens, this is luck, yeah? There's no deep physics behind this, but luckily, very, very many of the lines that exist here actually come from pretty hot stellar plasma. They are mainly formed at 2-3 million Kelvin. And if anybody here happens to be an X-ray astronomer, those are also the temperatures where you directly derive your observable X-ray spectrum from. It's at quite different wavelengths, but the plasma and its temperature that causes both the X-ray spectrum and this small snippet of the EUV spectrum that's relevant to exoplanets actually come from very, very similar plasma temperatures. So if you take that into account, you can actually do a much more reliable reconstruction of what this part of the EUV spectrum should look like than just merely interpolating from a bunch of things. So this is something that we are working on in my group a lot right now, and that I'm very excited about, that stellar physics is so relevant to the exoplanets. This is a thing that has been popping up over the past, I don't know, 20, 25 years. You always end up back with stellar physics when you want to understand your exoplanets, which makes me very happy. I think the future of exoplanets in general, not just with the evaporation, but in general, if we actually want to go towards trying to find signatures of life, which is actually in many of the big observatories a stated goal. We have a bunch of homework actually to do. We might do this, what I'm currently looking at. We want to understand what's actually happening with these atmospheres at relatively early ages, what is happening, how efficient are we with evaporating something, and what should we actually expect, which planet should we pick to look at. But of course, there is also a lot of work to do with actually defining what a biosignature might actually be. So there's actually lots of things happening in the community at the moment here. So for the future, I think on the side of stellar physics, there is a lot of interesting work to do on understanding what the space weather actually looks like that surrounds the exoplanets, especially, for example, now with the Plato mission soon launching, we actually have access to a field where there are also many bright stars, where we can characterize things properly. We have some interesting opportunities here. From sort of the more high energy side, I think for me, still New Athena will be relevant. I would really look forward to an UV space-based observatory, but we will see how this develops in the future. It's always hard with space missions. On the side of the star-planet interactions, I think after many, many years of searching, we now have some really exciting first solid detections of these effects. And especially with the type of data and the amount of data coming in, we can actually try to tease apart the various statistical effects of stars doing their stochastic changes in activity as they do, versus things that are actually caused by planets and that you can pick up if your time series are long enough. For the exoplanet atmospheres, yes, of course, mass loss is an interesting thing and something that's also very accessible right now to study. I think for the big quest for biosignatures, I mean, I think many of you will have seen that if you're in the exoplanet field. So last year there was already a claim of a detected biosignature from a British team that was very quickly disputed, and I think rightfully so, by the broader community. But I think there's something that we as a community have to work on to say, what are our standards for actually saying we see a biosignature? What is our confidence level in on the data side, kind of traditionally, yeah, what is the confidence in the signal and what's our confidence in the interpretation of the signal that we see. And I think there we still have a bunch of work to do in the coming decade before we really start operating the next biggest level of telescopes to try and go onto the hunt for those observable signatures. So I want to close with something that's always very important to me. Of course, the science is always very exciting, but something we should never forget is that science is actually done by people. This is much more strongly now a part of my work as a director, because of course you have to create an institute and an institute culture that makes people happy and content to come to work and do their best work in a supportive environment, and that's very important to me. And so I wanted to close with this picture from last year's barbecue. And with that, I want to finish my talk, and I'm happy to take your questions. This is definitely something that we and other groups are looking at. So it's very possible that you might see also evolutionary different helium content there, basically. So a lot of people are studying some helium basically depletion, yeah, and you can look at that. I would say it's very much an open question. I think in the end we will need to look at various pathways that can explain why in some of those cases we just don't see a signal. Yeah, I would say from experience, in most cases it turns out to be a mix of several explanations. But I think the stellar radiation environment has a nice thing that we can actually study it relatively clearly if we can reconstruct it. So that's where we're going first, in this direction. Yeah, so actually out of the planets that I study most in my group, most don't actually fulfill the criterion of the habitable zone. I mean, the stuff that we are doing is really, we take the hot Jupiters or other, let's say, Saturnian or Neptunic planets and basically use them as a template to understand those evaporation processes, because we can see them there with a big signature, much bigger signature. If you take then basically the whole solar neighborhood, yeah, you can basically look into the white papers for the ELT. Yeah? People typically pick a golden sample, kind of like we do for Andes, where there's 5 promising exoplanets that are temperate and that will receive some more characterization that is currently possible with the facilities that we have, and that we might just give that our best shot. 5 to 10, something like this is typically the thing where it falls into a volume that you can actually probe. The whole star is bright enough, and you have the correct temperature. So I think even with the next generation, we do need a little bit of luck. Yeah. Flare. Honestly, this is not something I have thought about. People sometimes think about polarization signatures, for example, in reflected light of exoplanet atmospheres. That's something that people have looked at. It's not fully obvious to me what I should be expecting for a planet-triggered flare in terms of polarization. So it's something I should probably think about, yeah. This is true, yeah. I mean, one thing that tends to be a bit hard is, of course, if you want to do this, right, you need a spectropolarimeter, and you basically have to sit there and do this for 70 nights or so on something like Harpspol or Pepsi-Pol or something like this. Yeah, but I'll think about it. Yeah, I'll think about it a bit more. Maybe we chat when you come to Potsdam next time. Huh? Yep.
So close in that the environment doesn't play a role.
So for the types of planets that we study at the moment, basically it's so close in. I mean, they're always inside the astrosphere. But honestly, our knowledge about astrospheres is very, very limited. I mean, so one of my staff members works a lot with Brian Wood in the US, and this is a guy who has pioneered this technique of basically detecting astrospheres basically through absorption features in the hydrogen lines and so on. So there is, I would say, 15, 20 stars where we have some rough idea of the size and orientation of the astrosphere, also with the rest of the ISM, and that is it. So I think there's much to learn there, and just because it happens to be unproblematic in that regard for my close-in planets, there can be planets, especially when you go towards more temperate things, where you have to start worrying about that, yes. So this idea has been floating around for a while, basically. As soon as people started publishing about star-planet interactions, there was the idea of, hey, can we use this to basically infer that there's a planet? The attempts that I have seen so far, so there was also something on the radio detections a few years ago where there was basically based on certain radio emissions, there was an idea, oh, might there be a planet that has done this? And for those attempts, the planet hasn't shown up. But I think for very carefully defined subsets of stars, one can seriously think about it. Yeah. So in principle, I think it only makes sense to try and do this for stars that happen to flare a lot. Otherwise, even with larger surveys, you don't get statistics, and then you can start looking into it. I would still think if the planet is close in enough and fast orbiting enough that it causes such flare excesses, then I would hope with very long data collections, you would also find it showing up in RVs actually eventually, even though that's messy. Yeah, I don't have a good gut feeling which one would be statistically more powerful to see a bunch up of flares, or to actually try to do it with RV and try to deal with all the magnetic activity effects sort of on that end. Yeah. Okay. Yeah, okay. Let me clarify. So basically, typically in your stellar flare, let's say, here's my star, right? The front side, there is a flare happening. In white light, there's no beaming in any direction. It's basically just, you know, a hot black body and you just see it. So if you have your planet going around that causes more flares wherever it is going, you will automatically have basically half an orbit of the planet where you get to see the flares, and another half orbit where you don't get to see it. And this is basically what I mean with that. The planet doesn't know where we are, obviously. It's always triggering the flares, but for half of the orbit, we see them well, and for the other half, we don't see them. That is all that is meant. It's not a directional beaming or anything like that. This is true. This is a surprising thing. We didn't expect it to be sharp like that. So we'll see. We'll study it, what's actually behind it. I would have expected a much broader distribution, actually, yeah.
Thanks. I have two questions on the outlook part of the talk. On the space part, you said that we
So New Athena, I personally find exciting. I think we have interesting options there, especially because we will have much better access to high-resolution stellar spectra at basically lower fluxes. Yeah, this is great because high-resolution X-ray spectra currently you can only do for the really nicely X-ray bright stars. So I think this is great. This is something that can be done. Athena is supposed to be launched in 2037, so it's a little while to go, but not that long anymore, and then it slips a bit, you know how it goes, but it's going to happen, and I think it's going to be very interesting for characterizing basically the high energy environment of exoplanets. Yeah.
And on the ground-based part, you showed that AIP is part of building the UV part for this anti-spectrograph. So do you get a lot of guaranteed time for that?
Yes.
Wow.
Yeah, exactly. This is how it works for these consortia, right? You build your big instrument, you get guaranteed time. We're actually, in this consortium, we are not doing it snippet by institute, but really we are defining big science questions that we as a consortium want to investigate and then are picking the best targets. Because especially if you go for specific high promise planets, like also for the biosignatures case, this is really not something where you want to dish it out and distribute it. You want to actually combine this into something compelling. Yeah.
Okay. I don't see any last questions. Then, before we thank our speaker again, I think Joachim had a...
Yeah. We will take Katja for dinner at the Rossini restaurant at 7. Some of you have already indicated that they want to join. If there are more, please let me know. We have not arranged for drinks with students. One of the reasons is that Katja wants to see the solar-Earth interaction in terms of corona borealis, and we're not sure what to do. There's nothing.
No? Oh no. It's not dark,
Yeah,
it's true, but the
right.
solar activity doesn't look good, you say?
Okay.
We have a little bit of time until 7.
Well, one idea was to walk up Philosophenweg, although the part on the northern sky is not so good. The other one was walking up to the tower here with Ralph guiding.
Ah. Okay. It's not so dark. How do they do that?
Yeah.
Okay. Yeah, okay. Let's give it a try,
Okay,
huh?
so we are sort of spontaneous on that. The fixed point is 7 p.m. at Rossini, and if it's too bright or too cold, we can have a quick drink at Bar Deck so students can guide. I guess this is what we should do.
So come meet down here if you want to join for any of that. So
Very good.
with that, let's thank our speaker again.